Right. So quick introduction to the session. It's a session on streaming data to Azure. Some people ask me if it's streaming data like media services, etc. It's not. It's not streaming data out of Azure. It's streaming data into Azure. Right? And I'll quickly explain to you what it means. Right? My name is Praveen Srivatsa. I'm a director at a company called Azure Consulting. We consult on architecture, design, etc. I also play the role of a Microsoft regional director. I don't work at Microsoft. I am an external evangelism for them. Okay. Quick agenda, streaming data, something called Stream Insight, demos, Azure Event Hubs, different scenarios, and questions. Thought process, right? Largely, whenever we have been working with data so far, it's been data at what we call as rest, right? We enter data, somebody enters a whole form, somebody clicks a button, somebody comes back and does a data entry, right? So data entry is a term. We enter some data, we type in something and click to send an email, right? So we come back and enter data, and all of these are data which is relatively at rest. There's only so much we can click, right? We can't generate like a zillion emails per second per person. Right? So whenever we are dealing with data, even though it is decently large, even though the number of emails is large, number of tweets are large, etc., the amount of data that we can generate today it might be difficult to believe, but it's still very small. As we are going ahead, we are looking at data being generated by devices, right? So as an example, you have devices like you have Google Glass, HoloLens, etc. You've got mobile devices already. You've got bands. You've got sensors on shoes, etc. You have sensors, weather sensors, other device sensors. You have the whole IoT space coming up, right? Internet of Things, which are all multiple devices which send information. You can have your car sending information every second in terms of various parameters, right? How the engine is performing, what is the amount of diesel consumption, what is the speed it's going, what is the pressure of the tires, etc., etc. You will have a whole bunch of health devices which comes back and monitors heartbeat, your blood pressure, etc. on a regular basis and uploads it to the cloud. So the amount of data that we are looking at, which is streaming into the cloud, will become enormous. Right? And this is not trivial. In some instances, we see this already. As a simple example, a mobile operator, somebody like Airtel, Vodafone, etc. If you've got a mobile operator, the number of mobile calls happening through a tower is significantly large. Right? So if you want to come back and look at the log activity of a mobile operator, it runs into something like a few million transactions per second. Right? It comes back and say they aggregate somewhere around a terabyte of data every hour, right? And that is the amount of data that they start collecting when devices generate information. Just the fact that your mobile phone is active so that they can locate where you are, it sends a ping back, which means even if you're not using your mobile at all, it's still pinging the server, and the server is sitting and collecting all the data using which it has to come back and take some actions. Right? So the amount of data that we are going to be generating from devices is huge as compared to the amount of data that we are generating from human beings so far. When we come back and deal with data capture systems, traditional relational databases kind of a stuff, we talk of like 2000 transactions per second. We come back and SQL tops out at around 2000 transactions, Oracle tops out at around 2500 transactions on a simple setup, right? We come back and add a queuing system and push it to around 10,000 transactions per second to around 20,000 transactions per second, right? Really stretching it, you can probably push it to around 40,000 transactions per second, right? We are coming back and talking of millions of transactions per second here. We are starting at millions of transactions. So the whole area is something that is called complex event processing. The offering is there from multiple vendors. Oracle has a solution in this, SAP has a solution in this, multiple vendors have a solution in this, Microsoft also has a solution in this. So the complex event processing space is a space that says we will start at 1 million transactions per second, and the target, the current holy grail, is about 1 billion transactions per second. Right? So that's the space that we are talking of in terms of the amount of data or the amount of bits of information that is streaming into the system. Now remember, we don't just have to take all of this data and store it somewhere. We also have to take decisions based on that. Right? So if you want to come back and logically take decisions based on that, you have to query it, you have to search it, you have to aggregate it. So all our logistics of BI that we think of, wherein we store the data, then we query it, we aggregate it, we analyze it, etc. All of that is something that will be needed here. And if we come back and look at the traditional way that we are working, when we take all the data, store it, and then we look at querying and trying to do an analysis on it, it just will not work, right? So the whole area of complex event processing or data in motion is something that needs to work completely differently, right? And we'll take a look at that in terms of how it works. Quick question, how many of you have access to Twitter and you can tweet here in this room right now? Okay, I will need some help because some of the data looks at streaming data, so I will want you guys to add on to the streaming data so you can consume it, right? When I come to that, I'll tell you. Okay, different scenarios. While we come back and say Internet of Things and devices is a large contributor to this, this kind of a scenario is something that is already used. For example, financial transactions, the New York Stock Exchange has a system wherein it passes all the streaming data through it. It comes back and analyzes potential issues, right? People who have done multiple transactions, people who have done a sell and a buy in a very short period of time on similar instances. So it searches for a series of patterns. Now remember, it has to search through a series of patterns across millions of transactions that is flowing through. It's not yet in the millions per second kind of a space, but it is still millions in a few minutes kind of a space, right? And it has to look through all of these and analyze it for issues or potential alerts that it has to find out. This kind of a scenario is there in manufacturing today. If you want to come back and you have a car manufacturing system or you have a large assembly line, you have got other things that you are running through as part of a large manufacturing setup. You want every part of the manufacturing setup to come back and raise an alert to you in terms of how it is performing. You want to know that a piece has passed through junction 1 so that junction 2 is ready. If junction 2 is clogged, you want the rest of the things to pause or stop or reroute themselves, right? So most of this streaming data is also something that you want in terms of real-time analytics. So it's not something wherein you just stream and put it in somewhere. You also want real-time analytics behind it, right? And this kind of a scenario is there as part of real-time financial sales tracking, connected car scenarios or device scenarios, clickstream analysis, who clicked on what website, real-time fraud, data and identity services, and so on and so forth, right? So multiple different scenarios wherein this kind of a scenario is something that is required even today. So what is CEP, complex event processing? Complex event processing is different from regular database applications. Database applications, the query paradigm is we run ad hoc queries on stored data. In event-driven applications or complex event processing, there is a continuous stream of events that is flowing through, right? Think of it as, younger days we used to always start off saying if you want to understand object orientation, think of a car as an object, right? So if you track back to that example, you've got a large parking space full of cars and you want to query on it, that's a traditional relational database application. You've got cars which are streaming down the highway, right? That is what your real-time application is. And extend that to a Formula 1 race. They're all zooming past, extremely fast, but you want to collect statistics, analyze it, and take real-time decisions based on that, right? So the difference between traditional relational database applications and CEP is the difference between a large parking lot versus a Formula 1 kind of a race, right? So that's the differences in scenarios that we are looking at. Latency, seconds, hours, days. Event-driven applications, we are looking at latency of milliseconds, right? Something happens on a Formula 1 race grid, you want to know like in the next millisecond that there is an issue, so that you can come back and respond to that. Data rate, hundreds of events per second. Event-driven applications, we are looking at tens of thousands of events per second or more, right? And query semantics, declarative relational analytics, declarative relational and temporal analytics, and that's something I'll quickly explain to you what it means. So CEP scenarios have two things, aggregate data rate and latency, right? And the ones which have a large data rate and a very low latency are at the rightmost bottom corner, and those are the ones that typically qualify as CEP applications or event-driven applications. Okay. Typical CEP architecture, like in most integration standards, we have an input, we have processing, we have output. So it's pretty simplistic kind of an architecture, right? Event sources, multiple different event sources, devices, etc. You've got the stream insight application runtime, which is where you run all your queries, and you've got event targets, which is where you come back and send all the targets to, right? At a high level, this is the high level architecture diagram. Let me quickly run you through a demo, and along with that run you through the code, and then come back and map it to this architecture in terms of how all the pieces fit together. Okay. Now, in this demo, what we're doing is, it's a stream inside real-time dashboard. I hope I'm connected to the net. Okay. Now, I want you guys to tweet anything with the hashtag GIDS, right? Now, what this does is actually looks up Twitter data in real time. It has a filter based on certain tags that I've given. I've given Microsoft, I've given Xbox, I've given GIDS, I've given Skype, right? I've given a bunch of tags. I can change the tags, and we can come back and check in terms of whether other tags work as well. And what this is doing is it's looking real time for these hashtags, coming back, showing me aggregates, showing me rates, as well as it is inserting all of this into a table, and it's inserting all of it into a blob data store on Azure, right? What we can extend this to do is to come back and say, as part of this, also write into a Hadoop store, right? And come back and scale it out in terms of storing all the data. Now, also keep in mind, the Stream Insight engine is running on my local machine, but the Azure databases are in the cloud, which means there is a latency in terms of just writing onto the database, right? But that latency is something that does not affect the streaming data. One of the typical problems that we have got as part of relational database is, if my writes become slow, my input data starts getting queued up, right? And I'll just never finish processing it. In a streaming kind of a scenario, that does not happen, right? So what happens is, as the data streams, all the events are handled, and your writing is something that happens asynchronously at the background, right? It stopped. Okay, let me make it simple. Config. So let me remove everything else and just put GIDS. Right, so if any of you tweet with the hashtag GIDS, then it's something that it should pick up and come. So somebody did a test tweet. Who was that? Okay, right. So the point is, it is looking at real-time data. Okay, I just filtered it by GIDS so that we can see that it's actually looking at the real-time data. You can actually put a hashtag and come back and say there are trends that I want to track, and as part of Twitter information across the whole globe, it will come back and sync it in and pull it in. One of my friends, Janki Raman, is doing an IoT session tomorrow, Internet of Things, wherein he looks at integrating information from the cloud with devices. Now, there are interesting scenarios that we were discussing. For example, you could come back and put a globe and say, I will light up different parts of the globe depending on how much tweets are coming from that area, right? So I can actually have a round ball which tells me who is tweeting what about a hashtag that I've given, right? So I can actually connect all of this streaming data through my IoT kind of a devices to come back and have a real-time experience around it, right? So that is the thought process in terms of working with streaming data. The reverse also holds true. If I take Internet of Things, if I come back and take a BP monitor, a heartbeat monitor, we can actually, we don't have a device, but if we had a device, we could give a device to everyone in the room and come back and start measuring average heartbeat, right? We can come back and see what part of the demo the pulse goes up, what part of the demo the pulse goes down, right? I'm sure we can figure out, useless scenarios like this to come back and track, right? But the point is that Stream Insight or streaming data is something that comes back and consumes large amount of input data at extremely fast rate, analyzes that, and comes back and gives you different statistics around it. Now, 2-3 things I want to come back and explain as part of this definition so far here. Let me quickly walk you through the code setup first. Okay, as part of the code setup, we have got a Twitter client. Okay, I am very bad at this. I'm not sure if you guys can see the code. Oh, how do I zoom it? Okay, I'll just quickly explain it and then I'll tell you what's there. There are three parts of this, right? As part of this, we come back and define an application. We define a source. In this case, it is Twitter. So we basically read from Twitter. We compose a query on the Twitter feed. And in the compose of the query, we come back and say, I want to search all the tweets which have the hashtag that I've defined in my config file. That's all we are saying. We're filtering it. And we are adding a window. Every few seconds, come back and collect the data. But we also have multiple other queries. So we have a query for totals. I want a total by GIDS. I want a total by Windows. I want a total by Microsoft, right? So we have one query which says, give me all the hashtags. We've got a different query which says, give me all the aggregates. We've got another query which says, give me alerts. We can have a fourth query which says, check for a certain rules. Has somebody done a tweet with GIDS and with Microsoft in it, right? I can come back and have another kind of a rule, right? So we can come back and compose multiple different queries. So instead of having one query, we come back and have 20, 30, 50, hundreds of queries. Remember, all of these queries run in parallel. They are not sequential, right? So it does not matter how many queries you have. The stream engine comes back and hands it over to all of these query executions in parallel. So that is one part of it. Second part of it is the whole sink. Now you define where do you want to store it, right? You bind the source to the sinks, right? So you come back and say, I have a source, I run it through multiple queries, I take all of this and bind it to multiple sinks wherein I want to come back and store the data. Remember, every time I define a sink, it's an asynchronous process, right? It gets the data, passes it through the query. If the query is correct or it passes through the query, it goes back and stores into that data store. Which means by the time it actually does a I/O, by the time it actually comes back and writes into system, the aggregation is already complete, right? So it is pre-aggregated, the aggregations are stored in memory, aggregations are already displayed, and then it goes and writes into a store, right? So the whole point of a CEP system is that everything happens in memory. Writing to the disk is the last operation. Writing to the disk is a parallel operation. Writing to the screen and to the disk is something that happens parallelly. So you do the aggregate, say send it to the screen, send it to the disk. Which means by the time it hits the disk, you've already refreshed your screens and all other activities around it. If you want to take a decision, for example, trip a system in a manufacturing setup based on some rule, the data would have already come to the trip system even before it's actually written into a data store, right? So that's how it works in terms of sending all of this information parallelly, right? So three high-level stuff. There is a source. There's a bunch of queries that we write. It hands over to all the queries in parallel. There's a bunch of sinks. It sends all of them, all these queries outputs to those sinks in parallel, right? So that's how it, at a high level, it ends up working. So now if I have to switch back and quickly show this, now this sort of starts making sense, right? So remember, we have multiple event sources, right? All the data comes in from the event sources, but when it comes in here, we have input adapters which understands different inputs. So we have a Twitter adapter, we have a Facebook adapter, we have a device adapter. But when the data comes from here, we have a bunch of standing queries, right? And all the data that comes in is handed over to these queries in parallel. Now, what do we mean by in parallel? I get some data, I get one element of data, right? So somebody just tweeted with a hashtag GIDS, right? So there's a Twitter adapter, it reads the Twitter data, it hands over the Twitter data to the query engine, right? The query engine has to check whether it has got GIDS as part of its definition or not. And if it has got GIDS, it has to come back and send an aggregation to the GIDS tag, right? One of the key elements as part of the query definition is a floating timeline window. In streaming data, one of the constant things that we always need is a floating timeline window. We will have events that are lost. Somebody will tweet, by the time it comes, it will get lost somewhere, right? But what we are essentially looking at is, can you tell us tweets in the last 5 seconds? Can you tell us tweets in the last 10 seconds? Now think back to the scenarios I gave you. There's a Formula 1 race going on. After half an hour, that data is useless. After 10 minutes, the data is useless, right? Cars are streaming down a highway. After 15 minutes, the data is useless, right? Similarly, if I'm looking at who is tweeting what, half an hour down the line, that information is useless. I can take it from the data store. I already have it there, right? So the whole concept of CEP is it works on a timeline window. We have a timeline window wherein we define a start, we come back and we have a tick, we have a certain timeline window, and all the logistics that happens within that timeline window, right? That is the crux of most queries. Second, within that timeline window, it's always aggregations, right? It looks at an element of data, stores aggregations. It never queries across elements of information. So if I get a tweet, I compare this tweet against my aggregations. I do not compare this tweet against other tweets, right? So these are the two common elements that happen as part of all of that standing queries that we come back and generate there. Once we do this, we have multiple output adapters. We stream to all of them in parallel. We can process the output adapters depending on rules. So we can say if it has the hashtag gets, go write it, otherwise don't write it. So based on that, we send it to output adapters. All output adapters are in parallel, so they come back and write in parallel. But by that time, most of your operations is already completed and done. Okay. Quick thought process in terms of stream analytics on Azure. On Azure, it works very similarly. Azure has a service for the same called Stream Analytics. So as part of Stream Analytics, you have inputs, which is all the various input adapters that you want to work with. You have queries, which is where you come back and do all your filtering and your rules, right? So you say, based on the input adapter, based on the data element I get, I will come back and add a query, and you will add multiple different queries for here, and you define your outputs, right? So that becomes your engine in the cloud, which can come back and handle a large stream of data which is flowing through, right? Multiple input adapters. You want to target your own custom device, you will have to write an input adapter, right? Add a bunch of queries based on the data model, come back and say where you want the output to go. You want to go into you want to write the data into a big data kind of a data store. You want to write it into an analytic store, or you just want to update a screen. All of them becomes a sink that you write to. Okay. Key features that you get as part of putting this kind of engine on the cloud: connected, scalable, integrated analytics kind of a system. It collects real-time data. It does analytics using what we call as a temporal operation, and I'll explain that in a minute. It also has the ability to come back and do sequential operations like you do with standard relational database, so you can sort of mix and match what you want to do as part of the Stream Insight setup on Azure. Azure, being in the cloud, gives you a very scalable system. You can come back and do what is called as an auto scale, wherein you can say, if I'm getting so many inputs, if I'm getting so many events per second, have one instance. The moment it crosses a certain threshold, add one more instance, right? So you can come back and sort of guarantee that you will not let go of events by automatically scaling up in the server. You can also scale down. So you can come back and say, if I'm not getting so many events, come back and start knocking off instances and give me with a small set of instances to handle all the events on the cloud. Key thing that you get as part of Azure is you get a restful endpoint, right? So all the data inputs are a restful endpoint. Microsoft is also opening up to non-restful endpoints, a TCP/IP, a compressed port kind of a endpoints. It's also opening up to that, but currently that has some security definitions wherein it needs a certificate. You need a certificate on the device as well as on the cloud for them to come back and authenticate each other, right? But if you want to use a public kind of a definition, you use a restful endpoint. You take the restful endpoint, come back, pass it through multiple standing queries, and send it in. One of the things that Azure does is it provides a built-in archive, right? So if you decide that you don't want to put it into a data store and you just want to display it on the screen, but later on you come back and you are not sure what all data you got, right? Azure has an option to come back and just turn a switch on saying I want to keep a built-in archive, and you define how much of data store the archive should take. So you can come back and say, keep up to 1 GB of data, or you can say keep up to 1 hour of data, right? And it will automatically archive that for you. So that sync is something that is built into Azure itself. Okay. Key event models, right? When we are working with this kind of a event related data, we have to understand the way that we work with eventing data is different from the way we work with regular relational data. Like I told you, when we work with event-based data, we have large, dense data streams. It could be financial trading information, and you've got lots of events per second, right? These are typically streaming data, and streaming data pretty much always exists on a timeline. So your timeline becomes the most critical aspect in terms of looking at anything as part of streaming data. Events expose something which is called as temporal characteristics. An example of a temporal characteristics is time, right? This event was raised at this point in time, right? Within 5 seconds, that information is now useless, right? So there's a lot of things that events do which is very temporal in nature. Another example, I want to count the number of people in a room. I count the number of people in this room, right? In the next few minutes, that could change. Right? So everything that we do as part of counting aggregates, as part of counting information, has a context, and typically the context is time. You could also have other contexts. For example, you could have a context which is geolocation, right? So you can come back and say count all the people within a room, right? The room becomes the context. The moment people move out of the room, the count changes. The moment we shift the context to a different room, the context changes, right? Count all the people who are about to board a flight. The moment they board the flight and take away, the context changes, right? So whenever we're working with events, events have what we call as a temporal quality. The temporal quality is information that changes over time, and that becomes key in terms of querying for it, for us to come back and work with details around it. Hashtag GIDS as an example, I'm sure there'll be multiple tweets the whole of the last 2 weeks, right? If you want to go back and query that, that becomes a very long query. That becomes a very slow query. And that's a query that a Stream Insight system will not be able to handle, right? So Stream Insight or streaming data is not meant to handle historical data. It is not meant to handle data which was collected and stored before, right? You don't look at a data store to query it. You look at data in memory, and that's what you come back and query for. All of these interval events, you can have point in time events, you can have interval events with fixed durations, you can have interval events with initially unknown durations. Something that started, but I don't know when it's going to end, right? And you can have rich payload that capture all the properties of these events as and when they occur. In fact, most operating systems, as and when you move your mouse around and do events, there's a whole stream of events that is handling in the background, right? Mouse move events, click events, other system operation events, service events. There's a whole bunch of events that is handling in the background, right? Handling events is something that is quite easy for systems. Handling operations in a process is something that becomes slow. So the moment you take a series and put it as a sequential operation, it slows down the entire stuff. But the moment you raise an event, right, and the event has to be handled by 10 different queries, it will get handled by all of them at the same instance in time. So internally, the way it works is, the moment you come back and say hashtag GIDS, there is a query for that. The moment it gets a data which confirms to that query, it raises an event saying, I got a data element, right? Now the aggregation engine can take that input and add on to that, while at the same time the data storage engine can take that and add it onto the storage. So the moment you raise an event, all the consumers of these events are notified instantly, and all of them can come back and process this information parallelly. Okay. Different event types. In the Microsoft CEP platform, we primarily use the .NET types. All the events are structured and can have multiple fields. fields are typed using the .NET framework types, so integers, date times, etc. are all using internal .NET types. We allow for automatic conversion from a JSON kind of a model onto the .NET types, right? So we have a RESTful interface. Any data that's coming in a JSON kind of a format is something that can be translated onto a .NET type. One of the advantages with using a .NET type is you can also have your own complex models, right? So you can come back and say, if there's an event from a device, the device has a whole bunch of information, I can now create device as a model in .NET, and I can come back and say, take the JSON structure, map it onto the device class, right? So I can get all associated properties of that pretty much immediately. So if I have video streaming, I can come back and say, as I'm taking a video, capture information like time, capture information like geographical location, capture information like quality of the image, capture all of that as part of a complex type, which can be translated to a .NET type. Okay. The CEP engine provision timestamp field captures all the different temporal event characteristics. So you do not have a choice of ignoring the timestamp field. Right, so irrespective of all the properties that you capture, a timestamp field is pretty much mandatory, and that is something that will be embedded as part of the CEP definition itself. And event sources automatically come back and populate the timestamp field. When we work with event streams and adapters, a stream is a possibly infinite sequence of events, right? So it's coming, right? Cars are going on, Formula 1 race, the events are happening, people are tweeting. It's an infinite stream of events, right? You write an adapter to come back and gather data. The adapter must not store the data. The logic of the adapter is it should get the data and raise it to the CEP system and then forget about it. The adapter should not consume memory. That is the job of the CEP system to come back and figure that out, right? So the entire adapter has a certain interface and a certain specification that it has to adhere to. Right? So all the adapters that we write have to implement those set of interfaces to come back and ensure the data is streaming. Okay. Typical CEP queries. When we work with CEP queries, we can come back and say complex types that describe event properties, calculations that introduce additional types, grouping, aggregation, multiple event groups, etc., etc. In many ways, they end up being very similar to the relational queries that we come back and run, right? So if you look at it, we have projection, we have joins, we have exists, we have filter, group, apply, sum, count, top, etc. These are all the typical type of aggregation queries that we come back and work with a streaming kind of a data. Okay. You can use link. Link is language integrated query. So you can use link to come back and query for this data. So as part of this, you can use joins, you can use filters, you can use projections, wherein you select certain columns of that, you can use groupings, you can use a windowing kind of a setup, and you can use projects and aggregates. So how are these queries different from regular queries that we run? When we run as part of the query engine, relational query engine, we write a query, there is a query plan that is created. The query plan is optimized based on the data pattern, right? So it understands the existing data pattern, it looks up indexes and stuff, looks up how to figure out the data. Based on all of that, it comes back and creates an optimized query plan. Here, we're not even looking at stored data. All of this is data that's coming in memory, right? So if you use similar semantics to come back and query for that, how does it come back and even figure out what to do? How does it figure out in terms of how to optimize it? Right? So the whole logic of querying here, even though it looks similar, even though the semantics are similar, even though the definitions, joins, filters, etc. are similar, the way it works is completely different. Right? What is different as part of this whole engine? Okay. The key difference is SQL is a standard query engine. A CEP engine is like a RDBMS turned upside down. So the easiest way to understand it is in a regular relational database, when we are running a query, we store the data somewhere and we run the queries on top of it. In a CEP engine, we store the query and we pass the data through it. Right? So even though the semantics are similar, the whole execution model is completely different. Right? As part of the execution model, what we essentially do is we come back and say, instead of storing one query, store hundreds of queries. When I get an element, I will raise an event saying I've got an element with these characteristics. All the queries which need those characteristics will pick up the event, handle the event, process it, and take it further. Right? So in some ways, if you want to understand how a CEP engine works, it works the complete reverse of how databases work. Right? So the data storage, which is the IO part, which is the one where you take the biggest hit, is the last thing that happens. It never happens as part of the core engine. Right? Second thing, all the queries that we do as part of regular relational queries or even big data queries, they are largely sequential and in some case parallel, wherein we spawn off parallel, but we aggregate all the answers back together. Right? In a CEP kind of an instance, all of them are event based. There are no threads. There are no parallel processes. You don't come back and say, I will spawn off 4 threads. At the end of it, I'll aggregate all of them and get back. You don't do that. You raise an event saying, I got a certain data element. And whether it is 1 or 100 queries which have to handle that, they all do that instantly. Right? So there is no latency, there is no time lag, and the whole thing scales pretty much instantaneously when you come back and scale it out as part of handling large number of events as part of a complex event processing engine. It's a continuous execution model rather than when the query is submitted. So again, query is not submitted. Query is created upfront and kept. Data is submitted to that. Right? So the moment data is submitted, the event raises and it comes back and does all the aggregations. It uses what we call as an event pattern language and event stream queries. Right? So that is the fundamental difference between, even though the syntax is very similar, even though the link queries are very similar, fundamental difference between a database query or even a big data query and a complex event processing query is the fact that you don't look at stored data, you look at data that is streaming in as part of a memory object. You don't store the data and query it, you store the query and you pass data through that which checks whether it matches to the query or not. Right? So you sort of flip the whole thing around as part of coming back and executing a CEP engine. Any quick questions? Comments? They're all very similar. So his question is, there are some open source CEP engines. In fact, there are multiple CEP engines. Oracle has a CEP engine, like I mentioned. Other vendors also have a CEP engine, and there are a bunch of them which are open source. All of them at a high level work very similarly. Where they differ is their querying syntax. But all of them come back and handle events. All of them handle syncs. All of them come back and can handle millions of transactions per second. Right? The two things that differentiates Azure, one is the whole query language processing. It has a much richer language query processing at this point in time. Second is, given the fact that it's in the cloud, it has all the benefits in terms of cloud scalability. Right? So we can have 1 instance, 2 instances. You start a stream insight or a streaming instance with 4 instances, and you can take it all the way up to 4,000 instances. Right? So that kind of a scalability is something that is tightly integrated into the Azure cloud. Right? Other than that, in terms of the high level working, they're all very similar.
Is there any standard querying language for streaming?
Yes and no. So Microsoft believes Link is a standard, but that's not an industry standard right now. So like I said, the query engine part is something that is very specific to different vendors right now. In fact, there are some people who have come back and written proprietary querying engines which come back and say we don't even want to use the semantics like joins and stuff like that. Right? They have their own different windowing kind of a concept based on which they work. They might be slightly more complex, but they end up being more efficient. Microsoft has taken a stand that if you put the syntax very similar to what people are used to doing, then it becomes very easy for people to jump onto the bandwagon. Right? So that's the call that Microsoft has taken. But fortunately or unfortunately, the query engine part is something that's not very standardized right now. Right? I'm not sure currently if there's a need. All of them are standardizing the input and output adapters. Everyone wants to say that even if your engine handles the input, the output is something I can consume. So you can mix and match multiple CEP platforms together. Right? And that's something they inherently and automatically support. Right? But the query engine ends up being completely internal, so there's no burning need today to even standardize that. Right? So that's where the I would guess so, but I'm not aware of it. Right? The challenge that becomes is functionally time is one aspect that you want to query for, and there's a lot of logistics around time. But others are adding, for example, Microsoft has added on geolocation as an additional logic to query on. Now that is not something other vendors have done yet, right? So even the standards body will find it difficult to come back and figure out what all are the parameters based on which you want to come back and add on those kind of query logics, right? So I'm guessing it will take some time before that part sort of standardizes. Yes, there is. In fact, the sample is available as part of Codeplex, and the Twitter adapter has been custom developed, right? It follows an interface. You can take the same interface, and wherever it talks to Twitter, you can just talk to your device and implement a custom adapter. In fact, right now, there are very few adapters available, right? So expectation is that pretty much every device will either build a custom adapter or somebody will build a custom adapter for them, because the very few devices are coming back and giving out RESTful information. Right? The Microsoft Band watch itself does not necessarily give out a RESTful information. Right? So you'll need the watch SDK, and you'll have to build a stream adapter around it to gather the data to send to this engine. Right? So building adapters will become a large piece of work as we get onto this bandwagon. So that is one place where they have standardized. So the interfaces for inputs, input adapters and output adapters have been standardized, right? You will still have to probably touch up the code a bit, but large part of those code will be reusable. Okay. So as an example, Microsoft is also adding on a sample code for an Apple Watch adapter, where you can come back and take characteristics from an Apple Watch and come back and stream it into this, right? Microsoft Band has a bunch of data that it pulls in. You can write a bunch of adapters, take all of that and stream the data in, right? So if you want to come back and have something like a Microsoft Health or your own custom health platform, wherein you want to get data from multiple of these devices and aggregate it in, you will have to pretty much have all those adapters in place, right? Few small things to keep in mind. CEP platform characteristics. Whenever you have a CEP platform, one of the key things that you work with is event sampling. You can't practically work with all events. A CEP platform assumes that I handle zillions of events, but I'll still let go of some events. So you're looking at patterns, you're not looking at everything. It's not transaction oriented. So as an example, you can't count all the money that's going through and come back and add up and say this is the exact amount of money that will be transacted today, because some transactions could just flow out of the timeline window, right? In which case you will never see it at all. Right? So it is not transactional in that nature, but you typically work with a large set of events and you work with event sampling. Parsing, matching, transformation, enrichment, routing, storing. So the CEP engine is more similar to a ETL kind of a job, right? Rather than to a regular database kind of a querying job. A few examples of a generalized event language. Remember, even though the syntax looks like LINQ, it is not a data querying language, it's an event querying language, right? So few examples of an event querying language. Events need order numbers so that they can understand the sequence in which they appear. Events need attributes so that we can compare the values, and we always pretty much need a time interval, right? And typically we can use logical operators, time operators, sequence operators, etc., etc. When we come from a relational database query kind of a background, there are some things that becomes difficult to understand. So let me give you an example of how in an event-based system, the output would result differently as compared to a regular relational database system. One of the important operators is time and the sequence of events that happen, right? If events happen in a different sequence, the whole query will result in a completely different information. So as an example, let's take a sliding window example. I can choose to come back and say I will apply a filter and then a count, length equal to 5. So in this case, what I'm saying is, give me all the withdrawals where the amount is greater than or equal to 200 and the number of such events is 5. So in this case, look at what is happening. I got the first event, it was 500, so it added on to my event queue window. I got the second, which was 100, so it didn't affect it at all. I got the third, which was 200, so now I have W1 and W3. So I've got 2 events in my queue. and so on and so forth. So at the end of it, I end up having 3 events as part of my queue as part of this whole operation because 3 of them didn't match, right? Now, if I choose to apply the filter after the event queue, so if I swap the withdrawal amount and the length queries, I will get a completely different result, right? So if I come back and say where length is 5, where amount is greater than 200, what happens is all the data first gets into the queue, irrespective of what is the value of that, right? So first event came in, it got in. Second event came in, it got in, but it didn't get out. Third event came in, fourth event came in. So very soon what happened was I already have 5 events, even though only 2 of them have passed through. The 6th event, when it comes in, it will knock out the first event. So now when the 6th event comes in, it will come back and tell me only 2 events have matched what you wanted to see, as against the previous one wherein 3 events had matched, right? So you have to understand that conceptually this is an event querying mechanism wherein whenever you query events, events are streaming information. They have a timeline, they have a sliding window, they have a logical bucket in which they operate, right? Depending on how you add things onto the bucket and how you pull things out of the bucket, the whole query output will dramatically change, right? So that is something that you need to keep in mind. When you come from a relational background, you expect that if I say, length is this and this is this, it will always give me the same result, irrespective of how I look at it, right? But in this kind of a event processing window, that logic is something that is not always consistent. So you have to think differently when you're coming back and writing these kind of queries, right? So that was a quick definition. We have an extensively SDK. So people ask, can I build my own adapters? Yes, you can. Can you add on your own querying engine? Yes, you can. Even though Microsoft gives a query engine, we also have an option to come back and say, ignore the Microsoft query engine. I will tack on my own query engine. And you obviously can have your own output sinks as well, right? So technically, you can use the cloud platform when you can replace the input adapters, the query adapters, and output adapters. Just use the cloud container per se. Right? But Microsoft has kept it open to come back and say you can use any parts of this in terms of working with it. Right? Support for extensions in the CEP platform, user-defined operators, functions, aggregates, all of that is something that you can add on. You've got a complex aggregate or a complex logic that you want to implement, you can come back and implement logics like that as part of this definition. We have a temporal snapshot operator framework. This basically comes back and says that I took a snapshot, say the number of people in this room, I took a snapshot, right? Now from this time, I want to start relatively checking what is the scenario, right? So instead of just coming back and looking at a timeline window, I can come back and say, take a snapshot and look at relative differences from the snapshot, right? And that kind of a definition is something that is built into the engine itself, right? So key summary, streaming data operations are different from regular data operations. Right? Multiple ways that's different. We saw that streaming data comes back and does, from a scale perspective, they result in a much larger set of data per second than traditional data operations. Right? Also, the querying is much more complex with it. Streaming data can gather and manage millions of events per second. With devices and IoT, managing streaming data is something that becomes critical. Right? And Azure provides scalable capabilities to easily manage the streaming data. Right? So as and when you come back and look at mobile devices, you come back and look at IoT kind of devices, you will realize that managing the amount of data that it gives in is something that is a factor larger, right, than compared to the traditional ways that we were dealing with today, wherein we can take an input and write it into a database kind of stuff. Right? So the whole way of working with analytics, whole way of working with streams is something that will significantly change as we move into the whole IoT world. Right, so that's a summary. Questions, comments, if any? What is that? You have 3 buckets wherein you are charged in terms of number of transactions per second that you want to handle. Right? So it has 3 buckets. Auto scaling is also based on number of transactions. Right? So it's not based on data storage. Storage is a separate cost. You can choose to store or not. You can let Azure store, which it will store only temporarily, and it doesn't charge you for that part of the storage because it's only temporary. But all the rest you are charged in terms of transactions that you want to stream through it. Right? You have a bucket, so even though they come back and say streaming number of transactions per second, number of data elements per second, if, for example, some seconds you have more and some seconds you have less, it averages it out across an hour. Right? So average across an hour is what you are typically built for. Right. You also have the option of taking the whole Stream Insight platform, installing it on a local machine, and not installing it on the cloud. Right? So for example, you're doing dev, you want to test with some devices. Before putting it into the cloud, you can also download the whole Stream Insight engine onto a local system and come back and connect your devices and get it working, and then you can come back and put it onto the cloud. And the bandwidth charges also. That's also something that will get charged. Right? Okay, so it'll be interesting to write a complex event processing to look at billing for an Azure site, right? In terms of all the data that's streaming in, all the data that's streaming out, and how much your bill logically could be. Not specifically. The key pattern that we have to follow is the fact that we have to look at time window based stuff. If you look at everything, most of the information is given out as graphs, not at tables, as graphs, and all the graphs are timeline based information, right? And other than that, it's aggregates. But other than that, there's no other specific patterns that's there. Okay, so thank you. I hope it was interesting. Okay.
Thank you so much, Praveen, for